Hello, everyone. So today I want to talk about reactive programming, but not in the sense that it's great, and not in the sense that it's going to help you with your particular business. Today I want to talk to you about the dark side of reactive programming from my personal experience. So actually, after this talk, I would like you to make a conscious decision. So the main selling point of this talk is that you have to have a certain level of expertise in order to practice reactive programming. You have to be, metaphorically, you have to be this tall. Otherwise, you would just go into a big ball of reactive mud. And I will show you a few concrete examples. How hard can it be? So do you know from which popular movie this quote comes from? No one? Yeah, it's from Taken. It's Liam Neeson. He said it to a kidnapper of his daughter, but he could just as well say it about reactive programming. Reactive programming is this amazing set of skills that allows you to do some really, really cool stuff, but it can really hurt you and the people in your team. And I really have some experience with that. So who am I really? I don't typically do an introduction of myself. I just want to convince you that I do have some experience with reactive programming, reactive systems, which is kind of a different thing. So first of all, I built quite a few complex reactive systems. And I'm not really proud about the complex stuff. It's just so happened that they became complex over time. And that's part of the reason why I give you this talk. So I was building Akka clusters with more than 1,000 remote nodes. They were doing some amazing distributed banking computations. They were assessing risks of bonds, CDSs, swaps, all these toxic assets, and the investment bank was supposed to somehow figure out whether they are risky or not. And this had to be spread over a really large network. Okay. I managed to handle tens of thousands of requests per second on a single node. Using reactive programming, I'm still talking about reactive programming. I beat C10K problem. I'm pretty sure some of you know what C10K problem is. Raise your hand. So for those of you who don't, C10K problem is kind of an archaic problem at the moment. It basically means that you're supposed to, your task is to handle 10,000 concurrent connections at the same time, which is actually a non-trivial task. Having a single machine handling 10,000 concurrent connections at the same time. And with reactive programming, this is fairly simple. It's not passable with normal Java stack, because this would require you to have 10,000 threads, which is kind of an overwhelming number for typical JVM. When doing reactive programming, this is fairly simple. As a matter of fact, even C100K is not something extraordinary with reactive programming. And imagine that, having a single server handling 100,000 concurrent connections at the same time. And I'm not talking requests per second, but concurrent connections doing something. I even wrote a book about reactive programming 3 years ago, so I do have some expertise with that. And this gives me the position to actually be a little bit grumpy. And I will be. And my point here for this talk is not to kind of unconvince you that reactive programming is bad. I just want you to make a conscious decision. Alrighty. Do you know this Chinese saying or Chinese curse? It's not actually about. It's not a positive saying. You don't want to live in interesting times. When you say to someone, "May you live in interesting times," by interesting, they typically mean wars, famine, I don't know, some internal affairs, some political issues. You don't want to live in interesting times. You want to live in boring times. You want to live in times where everything is stable, everything is predictable, and everything works as it used to 10 years ago, 100 years ago. That's what normal people want to have. Unless you're like a political leader or an army leader or whatever, then you do want to live in interesting times. But this is not a good situation for a majority of people. So I changed this quote a little bit. And I'm saying, may you support interesting code base. And what does interesting means in this particular case? Well, you know what? You're doing a code review. You're looking at someone's piece of code. And you say, that's interesting. And today's interesting is tomorrow's WTF. Because what interesting can you see in a code base? Well, maybe someone has solved a business problem in an interesting way. He found a new business flow or something. No, that probably didn't happen. It's interesting because someone used some really, really sophisticated data structure or sophisticated pattern or a library that you never came across. And if you look at it for the first time, it's interesting. But only for the first time. And after a while, it becomes more and more painful. You see where this is going. Okay, so let me present you some really, really simple application. The requirements are that simple. It's not a hello world, but it's still something we can come across in almost every single CRUD application. So fetch user by name. If it's not in the database, put it into that database. So lazily store it. Then load a shopping cart for that user, count total items, make a payment for all these items, and then send an email containing this payment ID. This is dead simple. And you probably wrote systems like that many, many times. Of course, not exactly like this one, but you get the overall idea. So you give these requirements to a junior developer or to a developer that just want to deal with business cases. And you get something like this. Honestly, it cannot get easier than that. It's Java code. It would look almost exactly the same in Kotlin, Groovy, Scala, Swift, you name it. If you have a decent C-like language, or a C syntax-like language, in almost every one of them, it would look more or less the same. If statements, for loops. OK, I'm using Stream API, which is probably the most complex part of the source code. But I can hardly imagine any other implementation, maybe with for loops rather than Stream API. But this is as straightforward as you can imagine. If statement, lists, for each, and so on and so forth. If you give this code to a junior developer, the one that just came from the street and it's his or her first day at work, and you give an extra requirement to him or her, like apply a discount. If the total payment is greater than $100, apply a $10 discount. Or don't send an email if the shopping cart was too big, and so on and so forth. This is really straightforward. Even my mom could probably add this requirement because it's so pragmatic. So now let's make it reactive. And I don't know if you have some experience with reactive programming or not. I assume you don't, so we will just be following line after line. But if you do use reactive programming on a daily basis, don't fall out yet because we will get into nasty details in a second. All right, so how do you make this code reactive? And question aside, why would you make this code reactive? But, well, why would you ask such a question? You just have like a new library, so let's refactor to it. OK, so this is the first line, fetching user from a database. And that's OK. If you make it reactive, it's almost exactly the same. You would probably name a method differently, but overall, rather than returning a user, you're returning something of a user. If this is Reactor, it's going to be mono. If this is Java 8, then it's going to be completable future. It can be a future in Scala. It can be an observable or single in RX Java. I don't really care about the framework or the library. So here's the first approach. And that's fairly simple. On these tiny details, and sadly, this is where most blog posts stop, this is trivial. OK, so let's move on. I want to make sure that my user doesn't exist in the database yet, or I want to test the existence of the user in the database. So what do? Rather than returning Boolean, I'm returning mono of Boolean. And if you have no idea what this mono is, it's basically just a wrapper that gives you a promise. In the JavaScript land, it's called a promise. It gives you a promise that sometime in the future, you will get a Boolean, because the computation happens asynchronously. And that's the whole point of reactive programming, that you offload stuff into background. So the same happened with the user. You no longer get a user in a blocking fashion. You get a promise of the user that you will get a user sometime in the future. The cool part is that you can actually parallelize these operations, and this is the selling point of reactive programming. All right, so we have this mono of Boolean. Now we want to operate on it. We cannot just like take the value from this mono or from this promise or future or whatever. Because it's encapsulated, we have to like apply all this monadic, fiddly thing that happens on top of it. So here it is. It used to be a simple if statement. And when transforming this if statement into reactive programming, the idea for this talk arose, because that's how it looks. And there's actually a few other ways of implementing this particular if statement. I'm not going to be explaining every single line here. You can go to the slides later on. I will post a link. The problem here is that it's no longer that straightforward, right? I mean, you would be crazy saying that the second code snippet is more readable to you than the first one. And we just came to the second line of our original code. So I'm not going to go through all the lines. I'm just going to show you the final implementation. We started off here. This is our simple yet very powerful application. And it does the job. It does the job well. It just does exactly what it's supposed to do without reactive programming. I rewrote it, and it actually took me like 15 minutes to rewrite it in an idiomatic fashion so that it's fully reactive using the state-of-the-art Java reactive APIs. And what I came up with, and seriously, this is the easiest but idiomatic thing I could imagine, looks like this. It's just like flat map over flat map over flat map. And honestly, I'm not exaggerating here. This is how you idiomatically rewrite this code. And the reason is that the reason for this thing is that you no longer have values that you can operate on. You have values that are wrapped in promises, and these promises will get completed somewhere in the future. Some of these are running concurrently. There is no concurrency happening here explicitly, but it is. So, and by the way, this piece of code is reactive. Can you see what actually got reactive? What is the advantage of this code over the previous one? It's lazy. Someone said it's lazy. That's kind of a side effect, which is really important. But for the rest of you, do you really care for the fact that this is lazy? And what does it even mean? Actually, it sends emails concurrently, which is totally buried in the details of the implementation. So I literally saw some of you looking like this when looking at the source code, because we started off really easily, and then it really escalated from a very simple piece of code to an unmaintainable sequence of monadic transformations of something. And honestly, I'm not exaggerating here. OK, so what happened? We started off with this. We came up to this one. What really happened? How did we end up with this? And let's face it, unmaintainable mess. Do you know the term ubiquitous language? It comes from domain-driven design, one of the most important parts of domain-driven design. It's the idea that when you're writing code, when you're a developer, when you're a tester, when you're a business person, when you're a user, everyone, when sitting in the same room, and even when they are outside of the same room, they speak the same language. And this seems so obvious, but the bottom line here is that if your customer and if your business people are using terms like insurance or policy or an accident or a money transfer, your code should be screaming from almost every single line the same terms. Your code should be about whatever you're developing. And this still sounds like kind of obvious, right? I mean, why would you have a source code that uses different terms for an application you are programming into? And OK, so imagine you're writing an application about insurances. You're writing in an insurance company. Almost every single line should be insurance, policy, accident, claim, so on and so forth. If you're in a pharmaceutical business, you have drugs, you have pharmacies, you have fakes, probably. These are your domain objects. If you're working in, I don't know, a hospital, then you have a doctor, then you have a patient, and so on and so forth. If you're working in a blockchain industry, then God, please stop. But you get the idea. And what happens if you start doing reactive programming? I found this quote about functional programming, which I'm also kind of a fan, but not a dead fan. Like doesn't look at the consequences. So someone said, is semigroup, monoid, I don't even understand half of these terms. Are these things intrinsic to your domain model? Is your application about monads, Kleisleys, and so on and so forth? Most likely not, unless you're building an application for mathematicians. And in that case, your domain actually is about monads, monoids, and functors. And a very important quote about ubiquitous language. How on earth are you going to find domain experts who actually understand your code, understand your test cases, if your code and test cases is all about monad, monoids, and so on and so forth? I'm talking about functional programming at the moment, right? Because this is the essence of domain-driven design, that you are focusing on the domain, not on some arbitrary, artificial mental model like functional programming. But why am I talking about functional programming? Because you can say exactly the same thing about reactive programming. So I based this talk on the Reactor, which is the new reactive framework from Pivotal. But this applies to every other framework equally. Is mono and flux pervasive in your domain model? Is your domain model, is your business centered around monos and fluxes? Do you know what mono and flux is? These are infectious diseases. And I'm pretty sure you're not writing software about infectious diseases. So why every single line of my previous piece of code was about monos and fluxes and flat maps? That was the most common word in the code base. My code base should be about whatever I'm doing with my software, not about some framework detail. We spend so much time trying to get out of annotations or interfaces that are related to frameworks, yet our whole code base is centered around reactive framework. So I'm going to ask you a question. What is the universal measure of code quality? Once again? Yeah, I actually wanted to put that slide on the presentation. Count of WTFs per second. So how many times you do, excuse me? Readability, pretty much the same thing. So how many times you do, you say WTF when looking at someone's code? Which is a pretty good answer, actually. So simple, right? Readability, WTF, whatever simple means. I mean, do you actually have a definition of simple? It's like the weirdest thing to say about anything. That's simple. Because one time I was reading an article about, I think it was functional programming, and someone said that monad transformers are reducing boilerplate. And I'm pretty sure they do. I just have no idea what they are. And I'm giving this talk for like a year now, and still I'm afraid to check what's a monad transformer, even though I kind of understand what a monad is. And someone out there in the internet actually believes that this reduces boilerplate, so it makes the code simpler. And he's refactoring his application because it makes the code simpler. Okay, so what else? Tested. Who agrees that a good code is tested? It's like not very controversial, right? And actually I do as well, so don't be afraid to raise your hands, except that if you have a bad code, just the fact that you tested it, and probably your test code base is equally bad, doesn't make your code better. It might make it safer, not necessarily, but it might make it safer. It might make your code base concrete, and by concrete I mean you will not be able to make any changes to your production code because it breaks so many tests that you will either don't do a refactoring or you will just stay with whatever you have right now or remove your tests, which makes absolutely no sense. So I'm going to give you a few more hints. Open, closed, do you know what it means? Open for extension, closed for modification, something like that, right? It's actually part of a larger acronym, SOLID. And I keep being asked about what SOLID is during recruitment processes. I honestly don't remember. I think it's single responsibility, open, closed, the first one, list of substitution, interface segregation, dependency inversion. Wow, that's a mouthful. But there are a few other things that you can say about the universal measure of code quality. So high cohesion and low coupling. I still don't kind of recognize which one is which. Then you have cyclomatic complexity, which kind of brings you a really complex way of determining how complex the function is, in how many ways it can branch out. Then you have dry, don't repeat yourself, and many, many, many other criteria. But you know what? After doing many, many pull requests and reviewing a lot of code, I came up to the conclusion that the universal measure of code quality is boring. And this is not a joke, right? When I'm doing a code review, remember what was a bad sign doing a code review? Interesting. No, you don't want your code to be interesting. You want your code to be boring. When someone is doing a code review, and you get a comment that someone says, it's interesting. Wow, you use this framework in a way that I would have never imagined. That's a really bad sign. If someone's doing you a code review and reminds you that you forgot about a business case, like what happens if you have a shipment and inside that shipment you have low value and so on and so forth, that's a really good code review because it makes sure you're covering all edge cases. It makes sure your code is doing the right business and it's making money, or, well, eventually every piece of software is there for making money. That's a good code review. If your code review is about formatting or naming, that's okay. Formatting can be done automatically. Naming is an important part of your code review. But you don't want people to focus on the framework or on the methodology you use during development. That should be completely transparent. People shouldn't see a framework. It should be a scaffolding somewhere that helps you provide business value. It shouldn't get in the way of your actual software. So your implementation should be transparent. And so many times people were bragging about Spring or EJB or Akka or whatever, any other framework that was kind of interfering with business logic. Yet, we are jumping the reactive train, which essentially means every single line is polluted with reactive code, this way or the other. And while doing code review, you shouldn't really care about frameworks, syntax, design patterns. They should just get out. You should only focus on what's important, providing money in a piece of software. All right. Have you heard this myth about 10 times developer? I'm pretty sure you did. So a 10 times developer, well, many people try to describe what a 10 times developer is. My personal definition is to enable 10 other developers to work effectively. You might be a 10 times developer because you're producing a 10 times faster code, or you're producing code 10 times, the code is faster, or you're producing the code 10 times as fast. But you know what? If you're generating code that no one else can read, you're not a 10 times developer. You're just an asshole developer. All right. You have to ask yourself a question, what are you actually optimizing? Because the sole part of reactive programming, and this is where it shines, is that it optimizes hardware usage. And it's really awesome in that area. You can do more with less hardware. We're going to talk about it later on. But are you really optimizing the hardware, or do you want to optimize how your team is used? So I can imagine 3 ways in which you can split the cost of actually running software. It's the cost of development, so essentially the cost of all of you, the cost of developers, how much time and how experienced developers you need to have in order to provide a certain functionality. Then you actually have to run it somewhere. You need a server to run your application, unless it's serverless. But it has to have a platform. It has to have a real hardware where it runs. The more traffic you want to load, you want to handle, the more load you want to handle, the more hardware you need to have. It doesn't matter for the moment how it scales. And then there's maintenance. So if you're working in an agile company, most likely you're going through all these steps. You have to develop, you have to deploy it, and then you have to maintain it. These are 3 costs that you have to take into account if you're building real software rather than just hello world. So how does it look like in our ordinary blocking world? And by blocking, I mean typical Spring, Tomcat, Java EE applications, servlet environment, and so on and so forth. So I split these costs in a graph. On a horizontal scale, what you see is the traffic. So how much load you actually have to handle, how big your company is. in a sense. Starting from a small company, then you have a medium size, and then you have a large corpo or whatever it is. And then I split the costs, so you can see how the costs are growing depending on the load you have to handle. It always somehow has to scale. So in the beginning, you don't really pay much for developing the software. Any framework, any language would do. Any framework can support HTTP, any framework can support storing things in the database, parsing JSON, and so on and so forth. You don't need a lot of hardware, and there's very little maintenance because you don't have a lot of code. However, once you start to grow, and you're really handling a massive load over time, you see that, first of all, the cost of software development grows because the system becomes more and more complex, but not in terms of business requirements, but in terms of scalability. It turns out that you can no longer use simple data structures, you can no longer use simple databases, you can no longer use a simple thread per request model, because it simply doesn't scale. So you have to try to figure out how to develop your application in order to handle bigger load. And typically at this moment you realize that your architecture doesn't scale linearly, which basically means in order to support 2 times the traffic, you need way more than 2 times the hardware. And that's the second area. The hardware also grows exponentially. 2 times the traffic, 3 times, 4 times, 5 times the hardware. And it just keeps growing and growing and growing. You can scale horizontally, which means buying bigger servers just to support your single monolithic application. You can, this was vertically. You can scale horizontally, so buying more servers, but this puts more pressure on developers, which now have to synchronize stuff, partition it, and so on and so forth. Surprisingly, the maintenance is still relatively cheap because the code is not as complex and it's a kind of a familiar ground. But what happens with reactive code? Well, it looks a little bit different. First of all, you need way more experienced developers. And by way more experienced developers, I mean, in order to start, you have to have a certain skills. Otherwise, you will just shoot yourself in the foot very, very fast. So on the vertical axis is the cost. The cost in some cloud coins. It's not in dollars because it all depends on your system. The initial cost of development is actually higher because you need more skilled developers and developers that actually spend more time trying to learn the actual reactive framework. There's no possibility that you are a good reactive developer without knowing the fundamentals that the blocking developer, let's call it this way, knows. So you have to be at a higher level, definitely. So the cost of software development is much higher in the beginning, from the very first day. However, once you kind of grasp the ideas, this code actually scales. It's way more complex, but along with your company, you don't need to tweak it so much because it's already designed to handle large load, which is a fantastic thing. And the same applies to hardware. You still need more hardware along with your company when it grows. But since reactive programming was designed from scratch in order to take advantage of hardware, so it doesn't consume that much memory, it uses way more CPU, so it consumes CPU equally and you don't run out of memory so fast. That's just great. So you invested a lot of time of your developers in order to save on hardware. And that's fine, that's kind of a trade-off. However, the maintenance becomes a pain very, very quickly from day one. And I will actually show you a concrete examples why maintenance is a nightmare with reactive systems. And if you've ever built even the tiniest reactive application, you know what I mean. Okay, as you can see, these two graphs have a slightly different shape. So you might ask a question, where do they cross? And by crossing, I mean at which point, at what scale of the application, reactive programming actually starts to pay off. The green bar, or the green line, is the cost of reactive system. At which point the investment, the initial investment, which is much higher into reactive system, starts to pay off. And that's a reasonable question to have. If your system's going to be small, if it's not going to be supporting so much traffic, why would you spend so much time, so much money, so much effort, so much blood and tears in the beginning? So this moment, when these two lines are crossing, I call it a Netflix point. This is just an arbitrary big company, doesn't really matter, I chose Netflix. It's the point where you reach the scale of Netflix, where it actually starts to pay off. If you're on the left-hand side, if you're smaller for a given set of measures, if you're smaller than Netflix, you won't get the return of investment on reactive programming. If you're on the right-hand side, it's probably foolish not to go with reactive programming. And as a matter of fact, clearly Netflix is on the right-hand side of the Netflix point, and they are using a lot of reactive programming. They actually invented RX Java, or they ported it from the .NET community. So I want to leave you with something here. So I want to help you with asking yourself a question. Are you really Netflix? If you're starting a new project, you have to ask yourself a question. Am I Netflix? Am I going to be handling the scale of Netflix? Do I need reactive programming? And there are many ways of evaluating it. I'm just going to give you a very small hint. Most likely, no. And, well, some of you maybe do. And I'm pretty sure there are companies that are of similar scale. And of course, Netflix is just a reference point here. You can put any other company here. Actually, I've been programming for more than a decade right now, and it's just the last company I work at where I can actually experience such a scale. And everything before that, it was just waste of my time and waste of my team's time. So most of the time, you should not invest because you're on the left of the Netflix line. Do you know Little's law? This one's going to help you a little bit more. Some of you do. I'm just going to explain it to you. It seems very abstract, but it's actually very fundamental when you're building any type of concurrent system. In Little's law, L on the left-hand side means the number of concurrent workers, thread, processes, single-threaded actors, whatever, or number of queues in a grocery store. It's very general. Lambda, on the right-hand side, is the average throughput. It's the average number of new customers, new requests, new packets coming in. So you want to know what is the average incoming traffic to your system. And W is the average time your system spends on handling a single request. So knowing the two, you can calculate the third one. Why do I even mention it? Well, it has some very profound consequences in our industry. For example, take Tomcat, the good old Tomcat. By default, it has 100 threads, 1 thread per request. This is the way Tomcat works since 2000. And it takes about 100 milliseconds to handle a single request, right? This is not overly optimistic or pessimistic. I guess any web framework can handle a single request within 100 milliseconds. It's parsing JSON, going to a database, and then marshalling JSON back. I guess any framework in the world can do this. It can do this in 100 or 200 milliseconds. So with these parameters, this single Tomcat instance can handle how many requests per second? 1,000. You don't need a Little's law for that. You kind of intuitively knew it. 1,000 requests per second. This is actually quite a lot. A single Tomcat instance on my laptop can easily handle 1,000 requests per second, according to the Little's law. Without reactive programming, just with this simple request per thread per request model. So ask yourself a question: what kind of load are you anticipating? Knowing the 2 parameters, you can calculate the third one. It's that simple, knowing just 2 or 3 numbers. Okay, have you heard of space-time trade-off? It's also from our industry. It's a very abstract term for something as simple as we are caching stuff, rather than computing it multiple times. We are spending some space in memory to avoid time. And by time, I mean time it takes to recompute something. And that sounds really simple. I mean, honestly, well, it's hard to disagree. Sometimes you wanna spend more memory. Sometimes you think that it's easier to go to a database or it's easier to calculate something from scratch. It's a trade-off. So it depends on use case. What I wanna show you today is a human-hardware trade-off. Remember these two charts? There were two forces: the cost of developer and the cost of hardware. At some point, it's better to spend more time on people, more money on people who are skilled to develop reactive systems, so that you benefit from less hardware, from smaller EC2 instances or whatever. However, in other cases, it's just a much better investment to have easier code base, to have cheaper developers, cheaper as in you don't need to invest so much time in learning them or in teaching reactive programming. And then you just put a few more servers and everyone is happy. And you have a very maintainable code base. Or you might want to make a switch at some point from blocking to reactive. You just have to precisely figure out when is this moment. Let's talk about maintenance. That was the third factor when we were doing our comparison. So when you're maintaining software, and I'm actually part of the team who goes from requirements, user stories, event storming, developing, testing, deploying, and maintaining software. And it's so much easier to see how your software behaves in production if you're going through all these steps during development. You will notice that reactive programming has quite a few disadvantages. First of all, I really started to miss stack traces. And that may sound weird, because stack traces are a sign of errors. But in reactive programming, they are a sign of errors. You just have no idea where these errors are coming from. So this is a stack trace I captured in IntelliJ. It has like quite a few hundred lines of stacks. Burj Khalifa, the tallest building on the planet, for comparison. And this looks terrible. I mean, if you look at the stack trace, and every other developer from any other language, when looking at the stack trace of a Java program, just like well, let's call it becomes really sad, because he sees hundreds of lines of frameworks and stuff. On the other hand, this is an invaluable tool when diagnosing what happened. Let me share you a story. One day, someone came up to me with this stack trace, and he was, well, observing something, exceptions related to a database driver. So he was looking at the stack trace, and what it says is, okay, I have a transaction something. I'm trying to get a transaction. I'm trying to begin a transaction. I'm trying to obtain a connection. And then I get a timeout of 30 seconds while I was trying to obtain a connection from a connection pool. That tells a full story of what the application was doing. If you go bottom, I would actually see the precise piece of code starting from a web layer, business logic, Hibernate, JPA, or whatever it was, up to the point where the error occurred. So even though the stack trace is really nasty, I almost knew what's going on. It seemed like the connection pool was running out of connections. So I almost knew that either I have a SQL query that takes too much time, or maybe my system is under a really, really heavy load, and I just run out of connections. Does this sound reasonable to you? My connection pool is empty, I'm trying to fetch a connection, and after 30 seconds, there were no spare connections in the pool. But I'm looking at the stack trace once again, and I'm seeing this. So let's examine it once again. And this actually happened on production. So I see that another thread, at the exact same time, another thread was trying to do a commit. All right, that's a reasonable thing to do. Processing commit, then there's trigger after commit, after commit, which actually surprisingly comes from my own class. And then there's Jms Template. Because I came up with this idea that whenever a transaction commits, I want to make a JMS mess. I want to send a JMS message notifying an external system that something has happened, which is not a bad design pattern after all. However, it turned out that sending a message is actually synchronous. So there's a blocking call called getResult somewhere in Apache ActiveMQ internals. And also it turned out, which sounds to me like a bug, but probably the Spring guys would say it's a feature, when you're triggering an after commit callback, you're still holding the connection. So even though you committed the statement, you're still holding the connection. You're not releasing it back to the pool. And it turned out I had hundreds of threads hanging on ActiveMQ because there was a problem with ActiveMQ broker. And how did it manifest? Well, because of how Spring callbacks are working, it was not releasing threads back to the pool, so other threads couldn't obtain new connections. Sorry, it wasn't releasing connections back to the pool, so other threads couldn't get them. It seems really convoluted, but I managed to get to these conclusions within 10 or 20 minutes, basically by just looking at the stack trace. So that was a success story. It turned out that the solution for an exhausted JDBC connection pool was restarting ActiveMQ, which is, well, not obvious, but it turned out to be obvious once we looked at stuck dumps. How would it look like if it was reactive programming? Well, first of all, stack traces are meaningless. Your threads your execution jumps between threads so many times in between that the stack traces are typically shorter, but they have no context. And trying to trace what's going on with your request from one thread to another is doable. It's just a little bit hard. You just have to add some extra measures like tracing or passing some context between threads. Otherwise, you will just lose focus and you would have no idea what's going on. It's difficult to follow requests because you have so many callbacks, you have so many events happening in between threads. And also, by the way, these are all quotes from Netflix when they were building, what's the link? Zool, which is their HTTP router and proxy. It's really hard to follow where the actual exception came from. The situation I was showing you in just a few seconds ago, it was really obvious what's going on. How does it look like in reactive programming? Let me show you. Let me show you some really, really simple example. This little guy, this is a typical reactive thing. I have a stream of something, and then I'm just applying 3 transformations on top of that stream. What bad can happen? Well, it turned out that one of these 3 methods returned null. And null reference is not allowed in Reactor. And RxJava 2, it was allowed in RxJava 1. And because it's not allowed, then Reactor will actually throw an exception somewhere telling him that one of the mappers, mapper is a function that maps, so you have 3 mappers here. One of the mappers returned null. How easy would it be to figure out which mapper was it? Virtually impossible. And this is RxJava. I put RxJava here just because people ask me what's the difference between RxJava 2 and Reactor. It's not big, to the point that even stack traces are very similar, and they are similarly hard to follow. Actually, Reactor is better. It has some callbacks, and it has some special mechanisms to track which part of the pipeline actually threw an exception, which is a good thing. But still, you get this. And notice that in both cases, not a single line in the stack trace actually tells you where the problem occurred. There are ways to overcome it. You just have to have a special set of skills, like Liam Neeson. Okay, timeout exception. Timeout exception is a blessing in blocking code, just like with the JDBC connection pool. It pointed precisely where the problem was. I could easily tell which piece of code was waiting for something, and then after 30 seconds, which is, by the way, an insanely big timeout, after 30 seconds, I knew precisely where it was interrupted. In reactive programming, and this is an example of Play, a Scala-based web framework, I have a timeout exception somewhere, and this is an anonymous actor in Akka, which I forgot to name, so now it's just a something. And once again, the pattern repeats. Not a single line from the output shows me my own code. It's just a timeout from somewhere. And once you start supporting reactive code, you will notice that these timeouts are actually a pain in your code base. Because what's going to happen is that you get a timeout exception, and very often you have absolutely no context. You know that something has timed out. And if you don't put a lot of logging, and if you forget to put some callbacks, some logging callbacks, you will find it really, really hard to figure out what's going on. Okay, but not to be grumpy, I'm going to give you a few best practices, because maybe you're already doing reactive programming and you just want to live your lives and do not roll back to the old world. So my first advice is that the best reactive system is actually single-threaded. And once again, this is not a joke. If you ask HFT, high-frequency trading guys, how are they making their programs so fast? They manage to say buy and sell stocks, shares, or whatever within microseconds. Their answer would be not reactive programming, not thread pools, not context switches. Everything just runs in a single thread. And this single thread is insanely fast. Our CPUs are now like 2 gigahertz, 3 gigahertz. A lot of CPU cycles can run within a single core. Once you start jumping between threads, it pays off if you're doing I/O, like calling a network, calling a disk, a file system, whatever. If you're just doing computationally intensive stuff, one core should be enough most of the time. So think about Reactor Pattern, which is actually a way of, I'm not talking about Reactor library here, I'm talking about Reactor concurrency model, in which you have a single thread producing, single thread consuming, SPSC, single producer, single consumer queue. You have actors which are essentially single-threaded. If you've ever worked with Akka, the core principle of Akka is that actors are single-threaded. You create thousands of actors, and every actor processes one message at a time, which simplifies stuff a lot. And then you have RxJava and Reactor operators, which are single-threaded as well, just for optimization purposes. So keep your code single-threaded as long as you can. Now, when doing reactive programming, you're going to be parallelizing or making concurrent a lot of stuff. And it's really, really easy to make stuff in different order than you actually requested. Because things are faster and slower, you have to pay a lot of attention to the order in which you get responses. And it's on a daily basis you will see situations where things are finishing in the order that you have never expected before. You have to understand what's the difference between flat map and concat map. Which one preserves order, which one doesn't. And what's concat map eager? How's it related to flat map? If you're doing reactive programming, think about it. If you're not, then that's just yet another thing you have to learn before you start physically doing it in your production systems. DDoS. Before reactive programming, actually everything was naturally throttled by Tomcat and its thread pools. Tomcat, Jetty, Undertow, whatever, could handle 100 requests simultaneously because it had so many worker threads, 100, 200, whatever. If you send more requests, Tomcat would simply start rejecting them. So it was a natural mechanism for throttling traffic. With reactive programming, you can actually handle hundreds of thousands of requests per second, and you can easily make hundreds of thousands of requests per second. Like the tiny flat map operator that you saw so many times, it actually has an implicit and very often forgotten parameter called max concurrency. By default, it's 128. And basically, it means how many concurrent processes it can spawn when running some business logic. It's insanely simple once you build a single component in your infrastructure. If you're doing microservices or SOA or whatever, a single reactive component can easily bring down the rest of your infrastructure because it's just so bloody fast. And you have to take that into account. It can consume an insane amount of traffic, but also it can very easily produce an insane amount of traffic, which means that either you have everything reactive, or at least you're capable of handling such bursts of traffic. All right, and monitoring. So once again, the part about maintenance. How do you handle monitoring of such systems? You have quite a lot of pain points. First of all, I really enjoy an architecture called SEDA, which is Staged Event-Driven Architecture. It stands for Staged Event-Driven Architecture. The basic premise is that you have a bunch of components that are communicating with each other via queues. So you have one component, rather than making synchronous requests, it sends messages to another component. It gives you a whole lot of new opportunities. For example, you can scale components that are not keeping up with the load. If you see that one of the queues accumulates too much traffic, you either slow down the producer or speed up the consumer. So in this type of architecture, you have a very simple way of monitoring the health of your system. You just look at your queues. You're just looking at how many messages queue up in front of every single component. And by the way, this type of architecture is very similar, for example, to ACCA actors. If you ever work with ACCA, this is precisely how they work. You have actors, they have mailboxes, you send messages to mailboxes, and actors are consuming them. And guess what? In ACCA, it's not possible to monitor the size of the mailbox. It used to be possible in version 1. In version 2, it was removed. They claim that it's hard to implement, it's almost never right, it's a parameter that they should not take into account, you should not monitor it, and so on and so forth. I almost trusted them that they are making the right decision by removing this single parameter. Maybe they are right, I thought. Maybe it's actually a good idea not to monitor the mailbox size. However, then I realized that they have this lightweight telemetry commercial products, and voila, it does have this parameter. So they removed it in ACCA 2, and then they added it to their commercial package. So it turned out it is useful after all. Timing. One more timing, and I have 5 minutes left. Timing things is quite counterintuitive with reactive systems. First of all, without reactive programming, I would simply say, this is a piece of code, please measure how much time does it take. And this is fairly straightforward. I just pass a piece of code, I run it, and I measure what was the start time, I measure what was the end time. This no longer works with reactive code, because reactive code is lazy and it's asynchronous. So if I measure how much did it took to call load user async, this would tell me that it took like 1 microsecond, because it's just the cost of calling a method, and all the processing happens in background somewhere in a different thread. So in order to actually measure, for example, in Reactor, how much time did it took from the moment you invoked a method to the moment you received a response, I have to go with this bloody thingy that completely obscures the business logic, which is somewhere, if you don't see it, is here. Right? This is your business logic, and everything else is just related to measuring time. So it's one of these things that it's really nice to offload into a framework. I'm just showing you how many traps you have to avoid. Okay, so key takeaways. Java syntax is not ready. It's better with Kotlin and coroutines. It's better with Scala and for comprehensions. However, Scala has its own set of issues. But it seems like in Java world, where you have fluxes, where you have observables, where you have completable future, it's just really painful to maintain. However, once Spring Boot 2 came out, everything changed. You no longer have a simple controller that, well, this is like the simplest controller you can imagine. Take something from a database and either return 200 OK or return 404 not found. Then you could sprinkle it with functional programming. So this is not reactive. This is just optional with map and or else operators. So nothing new. It's not as straightforward, but at least you're protecting yourself from null references. And then a new developer comes in. He heard about this shiny new WebFlux framework, which is great because it allows you to write these scalable web applications. But in WebFlux, and with these functional routing mechanisms, it's actually way harder to follow. And even though you are not convinced to use reactive programming, most likely you will have to support code bases like that, because now it's part of the standard. It's now part of the Spring framework, which I'm really grateful because I have a new tool. However, it's not always a good idea to use it. All right, so reactive programming is really awesome. And I'm telling it to you really, really honestly. I'm really serious. So reactive programming is really, really awesome, especially in the world where you have microservices and you have to call multiple services in order to construct the final response. Without reactive programming, your system just becomes really, really slow because everything is sequential. You just have to ask yourself a question. Are you really benefiting from reactive programming? Is it a need or is it a desire? Do you really need it in your production system? Or maybe you just want to put something new and shiny in your resume? You have to make a conscious decision. You have to think about your company in terms of the Netflix point. Thank you very much.